Good morning, and thank you very much for coming. My name is Valine and this is Panja. He will talk about American solar coronal, and it will be broadcast over internet, just so in case the people who want to attend and couldn't come can listen. Thank you very much again.
Okay, so for people who do not know what the solar corona is, so the sun on the corona is similar to the atmosphere of the sun. So on the surface of the sun, you have magnetic structures which are called sunspots, and there are magnetic groups which connect these sunspots. So I'm interested in the magnetic part of the solar corona. So this is this image is from one of my simulations. We don't use this anymore. I was trying to film some simulations, but we scrapped that idea anyway. So why do we need to model the corona? So some of you might know that the solar corona spews out vast amounts of magnetized plasma towards the Earth, and this in turn affects the magnetosphere of the Earth, and which that in turn can affect the electrical substations, satellite systems that we have. So it is important that we develop an understanding of the dynamics of the solar corona so that we can sort of predict the solar storms that are coming towards Earth. Now we do not have 3D observations of the corona. We do not have the 3D magnetic field observations of the corona. So which is why we are trying to use simulations to study the coronal magnetic field. Right, so there are several ways you can model the coronal magnetic field. One easy way to do is you have the magnetic structures on the photosphere, that is the surface of the sun, and you extrapolate that to find out the magnetic structures in the corona. It's like, suppose you place two magnets. So you know the field lines that will result from the magnets, right? So it's something like that. It's a potential field source surface extrapolation. The assumption here is that the corona is current free, that the magnetic field lines in the corona, they do not have any twist, they do not have any net current. So you solve these equations, curl of B equal to 0, and then you have the solenoidal constraint. And so you can, because of this, you can express this as a potential, and then you solve this to find out the magnetic structure of the corona. But and this is another way of finding out the magnetic field in the corona, which assumes that the corona is force field. The Lorentz force is 0, so it's sort of in an equilibrium, and you solve for this to find out the magnetic nature. But the problem is that you can only have extrapolations of the magnetic field at two different time steps, and there will be no connectivity between the two times. So you have individual extrapolations for different time steps. There will be no continuous evolution of the corona. So we choose a simple method of doing this, simulating that. It's called the magnetic friction model.
Excuse me, because we are also broadcasting the.
So I should stand here.
No. There's a small problem with sound. So please raise your voice and try to speak clearly.
Okay.
There's an echo.
Okay. So that's loud.
Yeah, loud.
Okay. Anyway, so we assume that in the solar corona, it is the magnetic forces that dominate and not the temperature and the pressure which determines the dynamics. So there are no large-scale flows that are observed in the solar corona, which is why we assume that it is only the Lorentz force, J cross B term, that plays an important role in determining what the dynamics of the solar corona. So this is our assumption. So this is the magnetic induction equation that I guess some of you are familiar with. So we write the magnetic induction equation in the form of the vector potential, where A is the vector potential, V is the velocity, B is the magnetic field, and J is the current. So this is our assumption. So since we assume that the velocity is determined only by Lorentz force, we take the velocity as proportional to J cross B. This is the magnetic frictional coefficient, which sort of determines how fast you want the velocity to be or how slow you want it to be. So this is, we fix this so that our code is stable. So if you have this too low, the velocity will become very high and your code will become unstable. So this has to be sort of fixed carefully. And this B square term is there so that in areas of even very low magnetic fields, you still have substantial magnetic frictional velocities. And this is another additional term which is put in by hand to replicate the solar wind. So there is a wind that flows out of the sun near the upper regions of the corona. This has been put in by hand artificially to model that. Right. So anyway, right. So the diffusivity in such models are very important because the system is non-linear. So the velocity is self-consistently determined by the existing structures in the corona. So to ensure that you do not have too high velocities can occur when you in places where you have very high currents. So to diffuse away the currents, we use very complicated diffusivities. So this is a diffusion term that we use. So the diffusivity sort of increases with the current. So when you have strong currents, to ensure that you do not have high velocities, you have to have high diffusivities to keep your code stable. So and this is the hyperdiffusivity term. So as you can see, this is proportional to the second derivative of the current. So which means if you have sharp peaks in the current, the hyperdiffusivity term becomes active, and again it sort of diffuses away the extra current.
Sorry, why do you have to use hyperdiffusivity? What is that?
Yeah, so otherwise, so you have spurious oscillations and things like that.
So for numerical reasons?
For numerical reasons, yes. Because you have to dissipate away the energy extra. So like if you had a full energy code, if you had extra current, that would have been dissipated away by probably an increase in temperature. That would have resulted in outflow, but you don't have that here. So if you get rid of that excess current that is being, because it can result in very high velocities, and that you wouldn't want that. And this is I should have actually given the references. So this part has been taken from Antony, papers of Antony's, and Mark Chin uses a similar hyperdiffusive term. So I'm solving it in r theta phi coordinates. So this is the sun, so this is r, this is theta, this is phi. So this is what my grid looks like. I put into, so there's a 2D matrix where I can put in sunspots, and the magnetic fields will sort of look like this. And this is my box is periodic in the phi direction for obvious reasons because the sun is circular. So I don't know if this is interesting. So when we use a staggered grid, which means that the variables are not located at one point. The variables are distributed over the grid. So this is the vector potential A theta. This is located on the ribs, and A phi and PR is. So this gives what this allows me to do is that this allows me to calculate the curl of A very easily. So the curl of A would be this minus this, minus this minus this. So del A theta del phi minus del A phi del theta. So which is why I use a staggered grid, and this ensures that I have a second order accuracy when I'm calculating the curl. Right. So how do I? So this is when I was trying to do full sun simulations. So I put in two bipoles initially. So bipoles are magnetic structures which are observed on the sun. So this has been all put in by 3D equations. So you have equations in the vector, a potential like this. This is a Cartesian-like coordinate system. So since I use a spherical polar coordinate system, I use an appropriate Jacobian to convert from Cartesian to spherical polar coordinate systems. So I put in something like this, and I let the system evolve, and you can see that connections have developed between the opposing polarities, which were not initially connected. So it's very simple. It's like, again, like you have two magnets. When you have one magnet, you have magnetic field lines. So when you bring in another magnet, you will have connectivities between the two magnets. It's something like that. So this is a closer look of how the field lines look. So here I have a video that shows sort of the connections developing. Right. So this is a 2D cut of the same photograph that I showed you. So this is what the sunspots look like when you're looking from top. So you have two bipoles placed side by side. And as you can see, the two things are happening. One, it is sort of fanning out in the theta direction, and the connections which were previously not there are forming. So essentially what is happening is it's moving towards a force-free state. So the velocity is proportional to J cross B. So when J cross B becomes 0, the system reaches a sort of quasi-equilibrium. I use the word quasi because you still have the diffusion term. So the system is trying to move towards the force-free state. So this sort of also resembles a potential field because initially you don't have any sources of current. So let me show you the. So this is the integral of the magnetic energy with simulation time. So the magnetic energy is decreasing and then it sort of reaches an equilibrium. And this is the kinetic energy integral of V square over the entire domain. So it doesn't become 0 because you still have the solar wind.
Can you make it full screen?
Yeah, sure. Right. And this is the integral of J square. The J is the current here. So again, as you can see here, it becomes quite close to 0. So it reaches the current free state, which means it is very close to potential field. So these were all done initially just to check whether our code is giving results that we think is correct. So similar studies were done in the past. So this is a paper where they used. So you can see they had initially placed two bipoles side by side, and then connections are developed like this. This is something at least qualitatively very similar to the results that we got. So there are more tests where I do not have enough time, so I'll not show you this. So all these were done just to check that our code gives results which matches with the existing previous results. So we developed a magnetic frictional model. So now we wanted to use twisting. So now, till now, we are not using any velocities on the surface. There were two sunspots which are just sitting on the surface, and we were trying to find out the magnetic field lines that would result in the corona from the surface magnetic field distribution. Now, what we are trying to do is, given a surface magnetic field distribution, we are applying artificial velocities to see how that would affect the coronal field lines. Right. So numerous there are evidences of observations of sunspots, observations of vortical flows that develop in the photosphere which tend to rotate the sunspots. So they are known to be. So these are some papers where they have done observational studies on rotating sunspots, and they are known to form sigmoid-like structures. So these are S-shaped structures which form when on top, just seen on top of rotating.
What are sigmoids?
Sigmoids are these S-shaped structures. It's sigmoid because because it looks like a sigmoid function.
But are they sunspots or?
No, they are sunspots. The sigmoids are observed in the corona. Right.
Okay, but
these are observed in X-ray, I believe.
Yes, but are they related to sunspots?
Yes, they are above. Yes, so that is what these observational papers suggest, that when you have rotating structures, they result in sigmoidal structures in the corona, which are observed in X-ray. Right, so we studied three cases. When one case is when you have a bipole, and two poles, and the whole thing is rotating about the center of the bipole. And the second case when one of the spots is rotating. A third case where each spot is rotating. They're sort of co-rotating. They're rotating in the same direction, but they're undergoing separate rotation about their own centers. So we simulated that. And so these are the sort of the first results that we got out of the simulations. Right, so as you can see here, so this is rotating and the field lines are also right. You can see the formation of an S-shaped structure. And another thing that is that should be noticed here is that it forms a tight bundle of magnetic field lines, which is called the formation of a flux rope. So here you see a formation of an S-shaped structure here, and it also, this is the top view, and this is what you see from the side. It also sort of expands in the corona. This is probably to release when it fans out in the corona, it releases the extra current that is in the system, and it helps reach a reach to a force-free state. This is the case 1. And this is a snapshot taken at a zoomed in snapshot taken at a particular time state, which shows the formation of a right. This is a snapshot that has been taken at an intermediate time state, which shows the formation of a kinked structures. Such structures are seen in observation as well. So this is case 2, where you have just one spot which is rotating. So this is the blue spot here, which represents negative, is rotating, and the red one is not rotating. So here again you see the field lines that are being twisted in response to the photospheric motion. So the difference between the case 1 and case 2 here is that if you notice the simulations, at one point the coronal dynamics, it becomes significantly faster than the photosphere. I mean, so we suspect that there is a runaway process that is going on here, right? So at around this point, exactly at around this point, things start. We see that there's a rapid change in the configuration of the magnetic fields, which we do not find in this particular case. So the field lines are evolving sort of more steadily, and we do not see a rapid evolution near the later stages of the simulation. So we just see the field lines twisting in response to the photospheric motion. And the simulations have been carried out for equal lengths of time for all the 3 cases. And this is the case where both the sunspots are rotating. Here again you will see the formation of a, it's sort of obvious because of the motion that has been imparted to the sunspots, and figure 8 sort of structure. But again in this simulation we do not see a rapid evolution of the coronal field lines, which we see in case 1, where after a certain point you see that there is a rapid sudden topological changes in the magnetic field lines in the coronal. So we did some quantitative comparisons. So this is the surface current. The surface current is a sort of it gives you a measure of how much twisted the magnetic fields are at the surface. So this is the case where the whole spot is being twisted around the center of the whole active region, and this is where one spot is being rotated, and this is where the 2 spots are undergoing individual separate rotation. So clearly a lot more surface current is being generated in the first case, which is sort of obvious. And this is the pointing flux. The pointing flux is a measure of the electromagnetic energy that is pumped into a system. So this is E cross B. So again, even in the first case, you see that a lot of energy is being pumped into the system. So this is the interesting part. So the helicity is A dot B integrated over the whole volume. A is the vector potential. So helicity, speaking loosely, gives you an idea of how much twisted your magnetic fields are. So what we see here is in the case where the whole bipole is twisted, it becomes positive and then it becomes negative, and it again becomes positive. So what we suspect here is that the handedness of the twist is changing. As we are rotating the sunspots in the surface, it's becoming left-handed, and it's again becoming right-handed, and gradually the helicity is decreasing. Whereas in the other 2 cases, we see a steady increase of helicity. So helicity is typically, it is believed that when you have eruptions, flux-slope eruptions, it reduces helicity, which we think what is happening in this case. Even in the subsequent plots, this is the current that is generated in the solar corona in response to the surface current that is driving the photospheric motions. So again, we see that in the first case, even though it increases sharply, it falls below the second case after a certain point of time. So again, this probably is a signature that the flux loops have been expelled in the first case. And again, this is the magnetic energy. There is again, you see, in the magnetic energy, this is the integral of B square over the entire volume. The magnetic energy rises more rapidly in the first case where the whole bipole is being twisted, and again it falls away quite sharply as opposed to the other two cases. So what we think is happening here is that when you're pumping energy at a faster pace, when you're introducing current at a faster pace, it leads to a process where a lot of flux strokes are ejected, and you have a rapid decrease in the non-potentiality of the system in the corona. Whereas if you do this at a steadier pace, if you twist the bipoles at a steadier pace, if you introduce current at a steadier pace, you do not have such a runaway process. So if you see this simulation again, although it sort of visually suggests that there are ejection of flux strokes, we are looking for definitive quantitative markers where we can tell that flux stroke eruption is definitely happening. So the work is still ongoing. So yeah, right around here. So you see a sudden change in the topology of the magnetic fields. Around here, you see visually suggests that there are flux strokes that are being expelled. But and that is what is also being suggested by the change in the magnetic energy and the net current in the system. But we are looking for definite quantitative markers by which we can tell that yes, that there have been eruptions indeed. And now we are using hypothetical velocities. So an improvement of the model will be to use actual real data where we can take photospheric flows obtained from real data and use that to drive our coronal model. So there is another question that we want to answer, that is there a threshold beyond which a runaway mechanism is activated? And in the future it is planned that we'll do full sun simulations, and so we need improved parallelization. So, well, thank you.
I don't know, just a simple question. The reason the sunspots are rotating is the granulation or something?
So I think there are local vortices that are generated because of you have small scale turbulent motions on the surface. So I do not really know much about the flows that are just subsurface, but there are, I believe, small scale flows that twist.
Is there random process?
There are random processes.
One spot is rotating, the other not, in a bipole. How do we explain?
So there have been observations where one spot is rotating and the other is not. But I guess if you have two spots and there is a vortex that happens to be at a position where there is just one spot, I guess it's just a coincidence and there is no particular physical reason why one spot would rotate and the other would not.
Just a side question, like, is there any systematic effects that are observed that give rise to preference in the sense of rotation in both hemispheres? Or it has, well, broadly speaking, can it be also due to the rise of the flux growth and that is twisted? So the intersection of a rising twisted flux with the surface would give rise to a rotating sunspot.
Well, the question is more related to why a sunspot would rotate. So, frankly, I do not know much about subsurface dynamics. So, what our aim was, given a sunspot would rotate, what would happen above? Yeah, right. So, yes. So,
can also be another reason. That's what I'm
so maybe I don't know. So the V cross omega term, the Coriolis force has a different direction in the different hemispheres. Maybe that can give rise to. So what we
So as an equation, so what's the knowledge you can use this result or trying to predict the form?
Yeah, so that is what the long-term plan is. So I'll be not working on this model, somebody else will switch to actually taking, so you have observations available of what is happening on the surface of the magnetic fields, how they evolve. The idea is to eventually get to a stage where you can use real-time observations to simulate what is going on. But that needs a lot of additional work.
Thinking about climate change, so we can really from the atmosphere not high voltages for simulation about the climate change is possible.
I'll maybe just speak to you after. I don't understand your question. Thank you.
It's in this, so we'll just.
Wireless audio.
Yeah. No, let it be. I'll run it. Yeah. Use that.
If you want to change,
This is
echo forward.
this is
Forward.
So, good morning to all of you. I'm Dr. Paniveni U.Shankar from the Department of Physics, NIE Institute of Technology, Mysore, India. And first of all, let me thank Istanbul University for giving me this opportunity to present my work in the field of solar physics, that is particularly in solar convection area. And the topic of my talk is supergranular parameters. The pictures that you are seeing here are the intensity grams and the Doppler gram. intensity gran is nothing but the intensity picture of the sun, and W gran is a map of the surface velocity of the sun. So this is my institute, and I have done my thesis work in Indian Institute of Astrophysics, Bangalore, India, and I am the research associate of Inter-University Center for Astronomy and Astrophysics, India. So the abstract of this present work that I am presenting is as follows. I study the complexity of the supergranular cells using the Doppler data. Doppler is nothing but the map of surface velocity map of the sun obtained using the solar and heliospheric observatory. And I also have used the intensity patterns obtained from Kodaikanal Solar Observatory. The chaotic and turbulent aspect of the solar supergranulation can be studied by examining the interrelationships amongst the parameters such as the length scale, horizontal flow velocity, lifetime, and the physical dimensions of the cells such as the fractal dimension, area, perimeter. The data consists of visually identified supergranular cells for which the fractal dimension D for supergranulation is obtained according to the relation P proportional to A bar D by 2, where P is the perimeter, A is the area of the cell, and D is the fractal dimension of the cell. And then I find that the fractal dimension is close to 1.3, which is consistent with that for isobars and suggests a possible turbulent origin of supergranulation. The cell circularity shows a dependence on the perimeter with a peak around 1.1 to 1.2 to 10 power 5 kilometer. I also study the dependence of the area of the supergranular cells with respect to the latitude, and I find that the cells are situated symmetrically above the 15-degree latitude. The findings are all supportive of Kolmogov's theory of turbulence. This is the plan of my talk. I gave a brief introduction, tour on the work done so far, data analysis, data processing, result, discussion, and conclusion. So, to give a brief introduction about solar convection. Observation of the solar photosphere through high-resolution instruments have long indicated that the surface of the sun is not a tranquil, featureless surface, but is beset with granular patterns. These cellular velocity patterns are a visible manifestation of the subphotospheric convection currents, which contribute substantially to the outward transport of energy from the deeper layers, thus maintaining the energy balance of the sun as well. Convection is the chief mode of transport in all cool stars such as the sun. Convection zone of thickness 30% of the solar radius lies in the subphotospheric regions of the sun. Here the opacity is so large that heat flux transport is mainly by convection rather than by photon diffusion. Convection is revealed on 4 hierarchical scales. On a scale of 1 to 2 arcsecond, it is granulation with a typical lifetime of say 8 to 10 minutes. And the next hierarchical scale is mesogranulation with a typical scale of 8 to 10 arcsecond and a typical lifetime of say 3 hours. And the next hierarchical scale, that's my area for the supergranulation with a typical size in the range 30 to 40 arcsecond and lifetime of about 24 hours. And the next highest hierarchical scale in convection is the giant granules, which have a typical size of 10 power 8 meter and a lifetime of about a month. Supergranules manifest regions of horizontal flow with a velocity 0.3 to 0.5 km per second, diverging from the cell center and with subsiding flows at the cell borders with a typical speed of 0.1 to 0.2 km per second. By virtue of geometric projection, such outflowing regions show velocity of approach on the side of the cell close to the center and on the side of the and they show the velocity precision on the side close to the limb. At the center of the disk, where there is no Doppler shift, it is almost uniformly gray. There's no Doppler shift here. And you see that the pattern is almost uniformly gray. And broadly speaking, supergranules are characterized by the three parameters, namely length, lifetime, horizontal flow velocity. Interrelationships amongst these parameters can shed light on the underlying dynamics. There have been extensive work in the field of supergranulation. Many authors have studied the temporal evolution and the study of the geometric features of these supergranular cells and the complexity of these structures. To name a few, it was as far back as in 1961 that Chandrasekhar has pointed out a relationship between the length scale of these cells with the magnetic activity. And it was in the year 1970 that Saikora pointed out a cell size dependence with latitude, as also confirmed by Raju et al. In 1998. And a dependence of the cell size with the magnetic cycle, solar cycle. The smaller size at solar maximum has been pointed out by Singh and Baku in 1981. And cells of a given size associated with remnant magnetic field live longer than those in the field-free regions, as pointed out by Raju et al. In 1998. And the lifetime of these cells are found to be larger for active region cells compared to the quiet region cells. Active region means the cells which are close to the sunspots. Quiet region cells means the cells which are away from the sunspots, or maybe no sunspots in the quiet region, quiet period of the solar minimum phase. So, this lifetime of these cells are found to be larger for active region cells compared to the quiet region cells, as pointed out by Raju et al. In 1998. And a positive correlation has been established by scientists Shrikant et al. In 1999. Convective motions and magnetic inhibition of motion are both stronger in active region cells, thereby leading to similar speeds in all regimes, as pointed out by Shrikant et al. In 1999. And recently we have shown that the velocity spectrum of the supergranular field very closely agrees with Kolmogorov's spectrum. VH equals epsilon power 1 by 3, L power 1 by 3. That is Binaries paper and 2002. And VH is epsilon per half, T per half, and epsilon here is the energy injection rate. And the slope on the log-log scale is 1 by 3, which is surprisingly compatible with the interpretation of supergranulation as a turbulent feature in the Kolmogorov model. We have also suggested a possible turbulent origin of supergranulation based on a fractal analysis. This is again our paper, Binaries paper and solar physics paper, 2005 and 2010. So the self-organization occurs on all scales, and this mechanism probably provides the intrinsic weakness of mesogranulation and the rare appearance of the highest hierarchical scale of the giant granules. So based on the inverse cascade of energy in a turbulent medium, a model of the solar convection encompassing all spatial scales has been proposed, and this is a very good paper by Krishan in 1996 paper. I have used 33R data full disk Dopplergram obtained on 28th and 29th June 1996 by the Michelson-Doppler interferometer on board the solar observatory. Of course, there is a solar minimum phase. And I have also used calcium 2K intensity data obtained from Kodaikanal Solar Observatory, India. That is solar maximum phase. 2001, obviously, it's maximum phase. But I needed both the minimum and maximum phase data. Both the Doppler-gram data and the intensity gram data have been obtained with a resolution of 2 arcsecond, which is twice the granular lifetime as well as twice the 5-minute period of oscillation. And also, the P mode vibration is very much reduced after time averaging is done over a period of 10 minutes. We do this 10-minute averaging which reduces the signal due to granular velocity flow. And our analysis, of course, rests on the implicit belief that time averaging removes noise significantly. And accentuation is borne out by visual inspection. And well-accentuated cells of the Doppler gram and intensity data line between 15° and 60° are selected. The choice of the data discounts error due to projection effects. That is the reason we have chosen this particular region of the cells, that is between 15° and 60°, so that the projection effects are completely avoided. Also, we have done this in the software program. We have eliminated this. We have done the correction for Doppler shift. That is done using a particular software program. So these are the precautionary measures which are taken before any analysis is carried out. Depending on the region in which it is found, it is called present or active. That is, it's closer to sunspot, it's active. Away from sunspot, it's present or white region cells. So regions that were not unequivocally present or active were avoided for simplicity. An example of the region and cell selection is depicted in figure 1. So this is 1. So this is the cell selection that is closer to the sunspot. This is the active region cell. This, and away from is the white region cell. Okay. And then this is the data processing of the cell area, cell perimeter, supergranular circularity, and supergranular latitudinal positions. These were carried out. So the profile of the visually identified cell was kind as follows. It chose a fiducial y-direction and performed velocity profile scan along the x-direction for all the pixel positions along the x-axis. Needs the scan, the cell extent is taken to be marked by the sum of the juxtaposed crest separated by a trough in the velocity scan. This set of points was used to determine the area and perimeter of the cell using, of course, the software program written in interactive data language IDEO. And so these points were used to determine the area and perimeter of the cell and the spectrum of all selected supergranular cells. I mean, similar methods are carried out to determine the area and perimeter of these supergranular cells. So I will show you how this velocity scan profile looks like. So this gives us the dimension, the size of the length scale of the supergranular cell. The distance between this and this. Sorry. So then, for solar maximum data, the fractal dimension of all the cells lies in the range 1.15 and 1.2. So for maximum data, I got lesser value for fractal dimension. For minimum data, I got a little higher value for fractal dimension. As you can see in this plot. So I'll show you later. Okay. The difference could be attributed to dependence of the network size of the solar cycle, the smaller size at solar maximum, as indicated by Singh and Bapu's paper, 1981 paper. I have compared the results of this fractal dimension of the cells, the solar minimum and maximum phases using MDI magnetograms, which is carried out by Derneği in 2004. It very well matches. My results are in full agreement with the Derneği's work. So the average dimension turns out to be around 1.3, which is consistent with that of isobars and suggests a possible turbulent origin of supergranulation. So area versus latitude shows a well-defined spread. The cells are symmetrically situated around 15-degree latitude. And a plot of the perimeter versus circularity also shows that the mid-range perimeter, 1.1 to 1.2 to 10 power 5 kilometer, is more circular. So probably this could be due to the fact that, as indicated in Shrikant's PhD thesis work, 1999 work, that it is dependent on weakening of the supergranular outflow pressure with radial distance. It depends upon supergranular outflow pressure, depends upon the radial distance. So more the radial distance, more is the weakening. So therefore, the larger cells are more correlated compared to the smaller ones. Smaller ones are more circular compared to the larger ones. It could be the reason because of that. And of course, the spectral distribution of the temperature, a passive scalar, is related to the spectral distribution of kinetic energy. It can be easily shown from Kolmogorov energy spectrum that both in 2 and 3 dimensions leads to temperature spectrum. Thus, the temperature variance varies as kappa 2 by 2 as a function of distance r. Then we fit our value into the Kolmogorov model, and of course, it turns out to be that 1.66 for an isotherm. But my work analysis has shown that it is almost equal to 1.3, which is same as 1.33 that you find here for an isobar. You see that this is 1.33, but I have got 1.3. So it means to say that supergranular convection is isobaric in nature and has possible turbulent origin. So fractal dimension varies strongly with size. Variation is not consistent with the data sets. I mean, it's different for different data sets. And also there is unsymmetrical variation of cell sizes with latitudes and circularity with perimeter. And there is non-monotonous variation of the fractal dimension with area. And of course, it's the most important work one has to carry out, and the modeling of this is to be done. So these are various references which I have used for my work. Of course, I have to show this. I'm sorry that. One second. I need something. I needed to show this the plot. It is lying from the pen.
So,
Huh. Go back. So this is the plot of circularity versus perimeter.
Do you have those figures separately?
Yeah, pretty much. No, it is there.
Files,
They are figure files.
but then you
Yeah, that's it is very sure. Yeah, here. Just scroll down. Yeah, I'm saying. Yeah, we will do. I think I just show these figures. Yeah. Okay. Okay, no problem. Okay, this is the plot, fractal dimension with the area in the solar minimum phase. which gives a higher value of between say 1.7 some such thing I got. It's between 1.5 and 2. And this is in the solar maximum phase, which is lesser, between 1.15 and 1.2. And this is the plot of the latitude versus area. It shows that the cells are symmetrically situated about 50-degree latitude, and we observe actually two minima at 20-degree latitude. And this is the circularity versus perimeter, which shows that mid-range cells are more circular compared to the extreme. Yes, and of course, it is explained very well because of the supergranular outflow pressure decreases with increasing radius. That could be the reason that the smaller cells tend to be more circular compared to the larger cells. Yes, that's it. And I'm very thankful to this Istanbul University for having given me this opportunity. We were very much disappointed that the 41st postcard had got cancelled for very obvious reasons. But in spite of that, the university did not disappoint us and it gave us this platform to showcase our work. I'm extremely thankful to the university. If you have any questions, most welcome.
Any question? How do you calculate the energy injection rate in the
That's a very simple mathematical expression that I have indicated earlier. It's done per half T per half. So it is like it is just a very simple lifetime, that is L by VH. Use that L by VH.
is the energy injection rate?
Yeah, distance divided by velocity.
The horizontal velocity.
Yeah. Horizontal flow velocity VH, and then L is the length scale of the cell.
But dimensionally, it's not energy per time.
Energy injection rate.
What do you mean by rate?
Pardon?
Per second.
Per second. Per second.
So it should be like joules per second.
Yeah.
But L is the length scale.
Length scale.
And VH is
VH is the horizontal flow velocity of the superluminous.
so it's L over LT, which
Yeah.
means just a dimension of time.
Yeah, I'll show you how I have calculated. I'll show it to you.
Thank you.
Welcome.
Let's take a break of 10 minutes. Coffee break.
Merhaba, biz izleyen katılımcılarımıza 10 dakika ara veriyoruz. Yayını kapatmayacağım. 10 dakika sonra devam edeceğiz. Buradayız yani.
Hazırız diyorum yani. Düzenleyebiliriz diyorum. Altyapımız var diyorum. 2 gün sürdürdüler.
We've got a data. Now we will put it on it.
Orada verelim şimdi.
Bir tane program böyle şey destekleri var da satışın ama öyle yapsanız bile mesela Türk lisede başvuruyorsunuz. Toplantıda program belli workshoplar belli olur. Şu teknik şey, otomatizasyon şey. Sonra bir de anlamsız programı görmediniz, programı aslında gelecek şey, geçen yıl bir önceki program buydu, önceki program budur. Program olunca vermiyorlar. Bu adam bu sözünü sanatçı program yok. Sayfa sayfa şu.
Very beautiful resolution. So then probably you're well, the doctor makes you
Simiden bağlı şu anda verdiğim var.
Şey, 3-5 gün önce büyük bir şey. Demişler ki
almost your right.
yakın eğer yıldızlar geri gelirse yıldızlar mahsul edebilmek üzere manzara
And your teacher.
Yeah, I just sit here. Yes, we need to see the focus murder. Here.
This is what you want.
Yeah, I know.
So,
thank you very much for attending. Are you leaving now or? One stuff, you'll be able to second you just go to the last step, you will see the statue
Thanks a lot. Thank you. But I don't know what figure files in my laptop. I was very comfortable. Check it. But anyway, finally I showed you.
not used to it.
No, but this one hyperlink. It's okay. Finally I showed. Yeah, I'll save this.
I mean, just in case.
Thank you. Thank you very much.
Goodbye. Also, you can walk around the
Yeah, you can. Goodbye. I'll give you my card.
Hayır şey tepkilerden İyi de verdim daha öyle yapalım. Biliyorum bak.
Biliyorlar. Dolu olduğunu var.
Diğer boşluklar, zemazlıktan sonra Ağustos boşlukları kimseye paylaşmıyor.
Tamam. Goodbye.
Sen Facebook'un şeylerine baktığında daha iyi bir şeyler falan böyle çok standart.
İyi bir şey oldu.
Şey yaptım, ben ziyarete sıkıntı bir şey yaptım. Ziyarete doğacağız.
Çok farklı film, olsa filmde neredesin? 19 çoktur.
Hatta yok.
Ya ben de pek olmuyor şeyler. Ben soru seviyorum. İlk hafta öncesi. $500 falan. Size bir şeyler varsa şöyle bir kendinden fikirli olan, mesela fikirli olan zaten bunun bir şey olacak, şirketten hisse. Bugün şey oluyor. Sinan başlayalım da yavaş yavaş. Evet, hocam söylüyorum. Sunum hazır olsun. Benim odada o var. Tamam başlayalım. Next one. Ammarin Pimnoo.
Okay. Thank you everyone at the Istanbul University. I'm Ammarin Pimnoo from Thailand. I am a researcher at Engineering of the Geoinformatics and Space Technology Development Agency. This is my organization. We are a government agency, government of Thailand about the space technology and development. Today, I would like to present the TR2 orbit design in the formation finding design in the coronal orbit and think about the damage prevention techniques for the South Atlantic magnetic anomaly. Okay. Before I go to the TR2, I want to introduce about the TR1 and talk about the design of the formation flying. Then I will go to the with this circle for the area coverage. That is the mission requirement of the satellite. And talk about the SAMA, the South Atlantic Magnetic Anomaly. So, and talk about the damage prevention techniques that need your comment. For the TRs, TEOS is the Thailand Earth Observation Satellite that is work initiated at July 2004 with the STM EADS STM funds as a builder company. This satellite was launched on the 1st of October 2008, and now it's end of life of this satellite already. So, but we still operate this. We still use the GIS data to support each of the organization or institutes in Thai government. The characteristic is this is a sun synchronous orbit, and altitude is about 800 kilometers. So the inclination is at 98.7. Local time is 10 a.m. The SWOT is the resolution is 2 meters and SWOT is 22 kilometers. The space program of Thailand, as I mentioned, so in 2008 we have launched TEOS-1, but from that 2010 until 2015 we developed only ground segment, excluding the system of the orbit determination, the system of the satellite control, even the antenna development, and also the optimism also is the system for gathering the image from all the satellite in space and download. Is for to make the image fusion something. But now 2016, the TEOS-2 had initiated, and we aim to have the AIT SMB indication testing, and we also have the 2 satellites. This all is the TEOS-2 projects that the very big project of Thailand now, and that is not only the procurement of satellite, not only 2 satellites, but also think about the solution based on the landslide, forest, and all fire. The satellite, this is just an example picture. One satellite is a very high resolution, about the 0.5 meter. Another one is about the 2 meter resolutions. We aim to now in the negotiations. So we will launch this together, or we will separate launch it. One is polar orbit, or another one is equatorial orbit. This is the technology demonstration. If the 0.5 meter resolution satellite is flying in the polar orbit, and the small satellite is flying in the equatorial orbit, we will use the techniques to divide the telecommand to another one. From the one satellite, send the command to another out of visibility of the antenna. This is our idea. So, especially we will use the AIS ADSB for communicate, identify the item on the sea or on the ground, and send the data to the air traffic control also. This is the TEOS-2 specification. We want to manage about the water resource, agriculture, marine, land, disaster, and mapping area, including national security, because of the big satellite is a 0.5 meter. That the object point to the military security. This is our facility. We have the Space Innovation Park at the Silacha near Bangkok. So including the satellite ground stations and the SMB integrations, testing, building, as well as the space inspiration for the awareness of the students or people who is interested in space. Okay, we go to the scientific story about the mathematical of the formation flying design. As I said, the TEOS-2, we aim to have the 2 satellites I record this one is a threshold 2 and this one is threshold 3. This simplify orbit formation finding design. We use the U equation method on its ordinary differential equation, and we can know about the trajectory of the two satellites. It will show us like a circle like this. When the circle changes, that means the formation, our formation is changing. So the differential equation of U with zero touch, and this one is with the force that we can put the force like a touching force or impulse or something like that. But for the Swedenborg and check with the two scientists from MIT, they have solved this method by include the J2 perturbation, that is the gravitational force, into the equation already. So we have many ways to get the linear solution. And another one, I got it by the use of Laplace technique. Use the Laplace operator, I can get the relative position and relative velocity. That's relative velocity very useful for the delta V requirement for estimate the touch to adjust the orbit between two satellites to keep the formation fine. This is the simulation, and this is the different displacements when I have simulated the distance of the two orbits in 10 days. So the distance is bigger day by day. My task is to have to reduce the amplitude displacement, and then I use the technique of to estimate the delta V, that I have to find the initial state, and then I find the final state, and then the total, we can do the total of the delta V requirement. I need to script this method, how to get that. As I want to show, this is the total, the table of the total delta V requirement of the formation finding. Anyone, if you want to know more, so I can present about this. Okay, after we can design the formation finding of the two satellites, after that is to design about the mission requirements about the Liping circle and the coverage image quality and on orbit validation, including the Gauss segment mission operation. This presentation I want to show about the Liping circle, that we need to get the image at the same time, at the same pace, like the ellipsis. The ellipsis, we have to consider the sub-orbit of the Gauss tag. So, and then we can estimate, we can calculate about the ellipsis time and about the field of discharge of the camera. This is the algorithm of the Liping circle. So maybe you, if you have ever to simulate the orbit about the 600 km altitude, you will have the about 14 something orbits in one day. The 14 something, that the something we can calculate that, and we can decide, we can use that for design the Liping circle. After I can design the orbit formation, finding orbits and requirement in the Liping circle. So I'm thinking about the where is the satellite have to face. The satellite have to fly through the area of the South Atlantic anomaly. Everyone know about this one, so that in the altitude higher about the 200 kilometers around the South Atlantic Ocean, we will have some kind like magnetic radiation storm, ionizing particle, including electron, proton, and area ionized. This is the simulation at the South Atlantic. So when our satellite flow past this area, maybe this area will destroy our electronic device, like a solar cell or sometimes like make the SEL or SEU single event laptop or single event. And this is the simulation of the electron flux. That is bigger than 1 micro electron volt at the 700 kilometer altitude. It's not only, so that means it's our satellite design in a polar orbit. The satellite have to press this area and this area also. But for the equatorial orbit, we will pass only this area. This is for the photon flux. This is the simulation of the ground tank. I simulate the two satellites flying in equatorial orbit, and this is the inclination of the 15 degree, and this one is 30 degree. So we can notice that when the low inclination, we have to fall past to the area many times in a day. So this is the high opportunity to we may get lost some maybe our calculations or something. I'm thinking about it, how to prevent this situation. So it's not because many satellites try to shielding the protection of the electric circuits on the ionizing radiation effect, or we used to protect the satellite and instruments. But for my idea, is not only that, maybe not enough. So maybe we have to turn on and turn off the satellites before going to the area. And when the satellite out of the area, the SAMA area, so we will start our electronic device again. But how to know the area when the satellite fall into the coordinates, the component X, Y, Z of the geometric fields can be expressed these functions. And we can know where is the high magnetic intensity. This is the simulation of the magnetic anomaly simulations. You can see this magnetic intensity very low. This is about the 0.2 or 0.28 is our warning. So that means 0.28 is maybe around here in this area. When the system detects the magnetic intensity about 0.2, that means we ready to turn our system off or start the system again. That bring me to the preparation techniques that I can write this. We have to know the ephemerals of the satellite and then calculate the magnetic intensity that I show you previously. And then think about the magnetic intensity is lower than 0.28. So that means we are in the SAMA region. And that's how we have to decide to go the satellite into safe mode and try to turn off the solar cell system and turn off the magnetic system. The system will check until the magnetic intensity is larger than 0.28, then it's larger. So start to require the GPS data and turn on the every subsystem and do that and do the operation again. So that's from the TR2 project. We have the two satellites on the orbits. We design for the formation finding and design for the Liping circle is the mission requirement. Then we talk about the SAMA region and have the simplified diagram, algorithm diagram to solve the problem. We will turn our system off when we fire in the region and turn it again when we are out of the region. This is the talk that I want to do today. Thank you. Question?
How long does it take, fractionally in an orbit for the satellite to stay in this area?
I'm trying to detect this by using this equation. So the problem is we have no sensor. Maybe we have, but we can use some kind like put all data into the big microprocessor and calculate this on board. This is the thing about that. But maybe we have to spend a lot of memory on the board.
Based on the simulations, what fraction of the orbit satellites goes through this low magnetic strength?
The fact is, actually I have the information about this. For a small satellite like a QSAT, is maybe we will have about 1 or 2 years. The damage will happen to the satellite, the single event laptop, or this one is to make about the digital 01, 02, something like this, but it chip our data. So maybe we will get the wrong information, or finally the circuit will make a short circuit because of the high electromagnetic will make a depletion region of our semiconductor. Yes, something like that.
I have a question. First is, in your system for prevention, you just shut it down. This means that the problem is when the system is operating.
Excuse me, questions.
If you shut down, there is no damage. Is that what you say?
Yeah, I see. But for my idea is we will for the power system is still working. The power system is still working, and the algorithm, this algorithm is also still working also. But for the other part, so we have to turn it off. But the problem is we cannot confident if we turn it off, and if it cannot start it again, that means we lost the satellite. But however, we have to many tests about that before launch. We have to confident it. But I also think about that.
Okay. Second question, could you show again this anomaly? Could it be the other one? The other picture?
This one and this one.
Okay, right. I did just on that red spot. Should I be aware of that?
I think because of it, as I showed you about this one, so the when error bell. First, as far as I know, I think everyone know about this one, right? Because of our magnetic field from the south to the north, and this one is like a particle around the Earth. We call this one the Van Allen belt. And this point, first of all, I think that in this university, not seeing symmetry. Believe me, not seeing symmetry. It has some kind like a backbone. The belt protects the Earth from the high, like a solar flare. This point is inclined down into our atmosphere. This is about 200 kilometers. So that means if you not go higher than 200 kilometers, we say
I will not go.
not for that.
final quick. So do I understand correctly, the low, too low magnetic field strength is not good neither, right?
Again,
So too low magnetic field strength is not good neither. I mean,
That's
you
good, yes.
shut it off when it's too loud, right?
Yes, yes.
Yes. Let me show you about this one. In fact, though, I didn't show. This is the full paper of this presentation. This is the optics, communication, avionics, and thermal control. It has the in space we have the plasma, ionizing radiation, and magnetic fields. So we will talk about this. The magnetic field will destroy the communication system, like the solar cells and the awareness system. Yes. That is the reason why we have to protect our satellite from the area. Is this your question?
Yeah. Okay, can shift to the next.
Okay. The next presentation is about the, because as I said, from 2016, we have the TR2 project, but from now, in 20 years later, we think Thailand thinking about the national space program and the full system of the TR2 include the two satellite and also the facility testing and also the solution application. We in our ministry, the Ministry of Science and Technology, we think about the communication satellite also. On the other hand, I also contact to the Japan about the keyboard module on the ISS, the International Space Station. That means that we have many things about the space, and we aim to establish the National Space Program of Thailand. The presentation is I need to go quick because it's very specific for the Thai government. So we study about the Japan, Korea, China, and India also about their space program, how they establish the space program, and then we will use the method to develop our country. So the NSP will support the education industry, digital economy, GIS, and social, and as well as the military security also. We aim to have the 5 components for the space program is the communication, satellite system, and the Earth observation, and space economics. It's very important for about the space exploration and administration, right? Like NASA, something like that. Earth observations and space economy and space operations. And this is the national space policy. We try to develop our economy, space industrialization. So we choose have something like a law or legislation, policy guides. So the mission of the NSP is through the national space policy, communication, Earth observation, GIS,
space or for national security, space monitoring, space innovation, and finally is national aerospace. Let me show you this one again. Actually, I prepared a poster for the COSPA conference, but okay, this is the poster that maybe very small. So from Thailand, we think about the from sorry, this year is the Thai. It is for Thai. It is for Thai. It's not for Christian. Okay, about the 20 year later, we will have some highlight all over and satellite and astronaut also. Okay. Okay, that's all of my presentation.
So at 1:30 we will have one more open minute. If you want, we can all go together to lunch.
Right. And this is the integral of j square. The j is the current here. So again, as you can see here, it becomes quite close to 0. So the current, it reaches the current free state, which means it is very close to potential field. So these were all done initially just to check whether our code is giving results that we think is correct. So similar studies were done in the past. So this is a paper where they used. So you can see they had initially their placed two bipoles side by side, and then connections are developed like this. This is something at least qualitatively very similar to the results that we got. So there are more tests where I do not have enough time, so I will not show you this. So all these were done just to check that our code gives results which matches with the existing previous results. So we developed a magnetic-frictional model. So now we wanted to use twisting. So now, till now, we are not using any velocities on the surface. There were two sunspots which are just sitting on the surface, and we were trying to find out the magnetic field lines that would result from in the corona from the surface magnetic field distribution. Now, what we are trying to do is, given a surface magnetic field distribution, we are applying artificial velocities to see how that would affect the coronal field lines. Right. So numerous there are evidences of observations of sunspots, observations of vertical slots that develop in the photosphere, which tend to rotate the sunspots. So they are known to be. So these are some papers where they have done observational studies on rotating sunspots, and they're known to form sigmoid-like structures. So these are S-shaped structures which form when on top, just seen on top of rotating.
What are sigmoids?
Sigmoids are these S-shaped structures. It's sigmoid because I guess because it looks like a sigmoid function.
But are they sunspots or?
No, they are sunspots. The sigmoids are observed in the corona. Right.
Okay, but
these are observed in X-ray, I believe.
Yes, but are they related to sunspots?
Yes, they are above. Yes, that is what these observational papers suggest, that when you have rotating structures, they result in sigmoidal structures in the corona, which are observed in X-ray. Velocity is self-consistently determined by the existing structures in the corona. So to ensure that you do not have too high velocities can occur when in places where you have very high currents. So to diffuse away the currents, we use very complicated diffusivities. So this is a diffusion term that we use. So the diffusivity sort of increases with the current. So when you have strong currents, to ensure that you do not have high velocities, you have to have high diffusivities to keep your code stable. So, and this is the hyperdiffusivity term. So as you can see, this is proportional to the second derivative of the current. So which means if you have sharp peaks in the current, the hyperdiffusivity term becomes active, and again it sort of diffuses away the extra current.
Sorry, why do you have to use hyperdiffusivity? What is that?
Yeah, so otherwise, so you have spurious oscillations and things like that.
So for numerical reasons.
For numerical reasons, yes. Because you have to dissipate away the energy extra. So, like if you had a full energy code, if you had extra current, that would have been dissipated away by probably an increase in temperature. That would have resulted in outflow, but you don't have that here. So if you get rid of that excess current that is being, because it can result in very high velocities, and that you wouldn't want that. And this is I should have actually given the references. So this part has been taken from papers of Antony's, and Mark Chin uses a similar hyperdiffusive term. So I'm solving it in r theta phi coordinates. So this is the sun, so this is r, this is theta, this is phi. So this is what my grid looks like. I put into, so there's a 2D matrix where I can put in sunspots, and the magnetic fields will sort of look like this. And this is my box is periodic in the phi direction for obvious reasons, because the sun is circular. So I don't know if this is interesting. So when we use a staggered grid, which means that the variables are not located at one point. The variables are distributed over the grid. So this is the vector potential A theta. This is located on the ribs, and A phi and PR is. So this gives what this allows me to do is that this allows me to calculate the curl of A very easily. So the curl of A would be this minus this, minus this minus this. So del theta del phi minus del phi del theta. So which is why I use a staggered grid, and this ensures that I have a second order accuracy when I'm calculating the curl. Right. So how do I? So this is when I was trying to do full sun simulations. So I put in two bipoles initially. So bipoles are magnetic structures which are observed on the sun. So this has been all put in by 3D equations. So you have equations in the vector, a potential like this. This is a Cartesian-like coordinate system. So since I use a spherical polar coordinate system, I use an appropriate Jacobian to convert from Cartesian to spherical polar coordinate systems. So I put in something like this, and I let the system evolve, and you can see that connections have developed between the opposing polarities, which were not initially connected. So it's very simple. It's like, again, like you have two magnets. When you have one magnet, you have magnetic field lines. So when you bring in another magnet, you will have connectivities between the two magnets. It's something like that. So this is a closer look of how the field lines look. So here I have a video that shows sort of the connections developing. Right, so this is a 2D cut of the same photograph that I showed you. So this is what the sunspots look like when you're looking from top. So you have two bipoles placed side by side. And as you can see, the two things are happening. One, it is sort of fanning out in the theta direction, and the connections which were previously not there are forming. So essentially what is happening is it's moving towards a force-free state. So the velocity is proportional to J cross B. So when J cross B becomes 0, the system reaches a sort of quasi-equilibrium. I use the word quasi because you still have the diffusion term. So the system is trying to move towards a force-free state. So this sort of also resembles a potential field because initially you don't have any sources of current. So let me show you the. So this is the integral of the magnetic energy with simulation time. So the magnetic energy is decreasing, and then it sort of reaches an equilibrium. And this is the kinetic energy integral of V square over the entire domain. So it doesn't become 0 because you still have the solar wind.
Can you make it full screen?
Yeah, sure.
Morning, and thank you very much for coming. My name is Valine and this is my Panja. He will talk about American Pimnoo solar coronal, and it will be broadcast over internet, just so in case the people who want to attend and couldn't come can listen. Thank you very much again.
Okay, so for people who do not know what the solar corona is, so the sun on the corona is similar to the atmosphere of the sun. So on the surface of the sun, you have magnetic structures which are called sunspots, and there are magnetic loops which connect these sunspots. So I'm interested in the magnetic part of the solar corona. So this is this image is from one of my simulations. We don't use this anymore. I was trying to film some simulations, but we scrapped that idea anyway. So why do we need to model the corona? So some of you might know that the solar corona spews out vast amounts of magnetized plasma towards the Earth, and this in turn affects the magnetosphere of the Earth, and that in turn can affect the electrical substations, satellite systems that we have. So it is important that we develop an understanding of the dynamics of the solar corona so that we can sort of predict the solar storms that are coming towards Earth. Now we do not have 3D observations of the corona. We do not have the 3D magnetic field observations of the corona. So which is why we are trying to use simulations to study the coronal magnetic field. Right, so there are several ways you can model the coronal magnetic field. One easy way to do is you have the magnetic structures on the photosphere, that is the surface of the sun, and you extrapolate that to find out the magnetic structures in the corona. It's like, suppose you place two magnets. So you know the field lines that will result from the magnets, right? So it's something like that. It's a potential field source surface extrapolation. The assumption here is that the corona is current free, that the magnetic field lines in the corona, they do not have any twist, they do not have any net current. So you solve these equations, curl of B equal to 0, and then you have the solenoidal constraint. And so you can, because of this, you can express this as a potential, and then you solve this to find out the magnetic structure of the corona. But and this is another way of finding out the magnetic field in the corona, which assumes that the corona is force field. The Lorentz force is 0, so it's sort of in an equilibrium, and you solve for this to find out the magnetic nature. But the problem is that you can only have extrapolations of the magnetic field at two different time steps, and there will be no connectivity between the two times. So you have individual extrapolations for different time steps. There will be no continuous evolution of the corona. So we choose a simple method of doing this, simulating that. It's called the magnetic friction model.
Excuse me, because we are also broadcasting the.
So I should stand here.
No. There's a small problem with sound. So please raise your voice and try to speak clearly.
Okay.
There's an echo.
Okay. So that's loud.
Yeah, loud.
Okay. Anyway, so we assume that in the solar corona, it is the magnetic forces that dominate and not the temperature and the pressure which determines the dynamics. So there are no large-scale flows that are observed in the solar corona, which is why we assume that it is only the Lorentz force J cross B term, that plays an important role in determining what the dynamics of the solar corona. So this is our assumption. So this is the magnetic induction equation that I guess some of you are familiar with. So we write the magnetic induction equation in the form of the vector potential, where A is the vector potential, V is the velocity, B is the magnetic field, and J is the current. So this is our assumption. So since we assume that the velocity is determined only by Lorentz force, we take the velocity as proportional to J cross B. This is the magnetic frictional coefficient, which sort of determines how fast you want the velocity to be or how slow you want it to be. So this is, we fix this so that our code is stable. So if you have this too low, the velocity will become very high and your code will become unstable. So this has to be sort of fixed carefully. And this B square term is there so that in areas of even very low magnetic fields, you still have substantial magnetic frictional velocities. And this is another additional term which is put in by hand to replicate the solar wind. So there is a wind that flows out of the sun near the upper regions of the corona. This has been put in by hand artificially to model that. Right. So anyway, right. So the diffusivity in such models are very important because the system is non-linear. So